So welcome back. In this video, we'll continue to discuss the variable elimination algorithm. But now we are more concerned with the efficiency of this algorithm and how we can make it more efficient for certain Bayesian network structures. So it's interesting to observe that the structure of the Bayesian network will have a large influence in the performance of the variable elimination algorithm. So just to mention one hypothetical example, let's suppose that we have two Bayesian networks, both with 100 variables. And it's possible to happen that when we find the elimination algorithm for the first Bayesian network, we find out that this elimination algorithm will have a width like 3. So it will be very efficient to compute the queries that we pose to the algorithm. At the same time, the second network, when we find the best elimination order possible, we find out that this elimination order has a much larger width, something like 25, and the performance will be much worse than the performance for the first one. Even though those two Bayesian networks have the same number of variables, one, for some reason, is a lot more efficient than the second one for the variable elimination algorithm. And that is not completely unexpected because we have discussed this before. We know that it depends on the structure of the Bayesian network. If the Bayesian network if the Bayesian network has nodes with large number of parents, we expect that they will have large CPTs, and they're going to be much more difficult to compute the results for the queries. So we are expecting something like this. But we needed to formalize a little bit better this idea. And the way to formalize that is with a concept that we call the tree width. So we are not completely define the tree width right now. We're going to define this in next lecture. But for now, we have a very intuitive understanding what is the tree width and how we could reduce that using pruning techniques. So the tree width, in a very intuitive way, it's a number that quantifies how much the network will resemble a tree structure. So the closer our Bayesian network is to a tree structure, more efficient will be the variable elimination algorithm. And we find that no elimination order can have a width that is smaller than the network tree width. So in some sense, the network tree width is a lower bound to the width of the elimination orders that we can find. And we will also find that there will be one elimination order. It can be more than one, but it's guaranteed that exists at least one elimination order that has a width that is equal to the tree width. So, but to find such elimination order is an NP hard problem. So it's going to be difficult to do it. So that is, again, shows the importance of the heuristics that we discussed in the previous video. Those heuristics are not able to guarantee that we're going to find the best elimination order possible, but at least they give us an elimination order that performs very well on average for most cases. So in practice, they are used very frequently. So let's take a look on the next slides on a few examples of Bayesian networks and their corresponding tree widths. So this is the one first example of a network and its corresponding tree width. So this network really reminds us of a tree. If you can think that this is the root node, and we have 3 nodes in the left side and 4 nodes in the right side. So it's very close to what our general understanding of a tree, with no loops and anything like this. So the tree width is going to be a number. In this case, for this example, is 1, and remind us how much the network looks like a tree structure. We can see, and we will define this later with more care, that the tree width can be defined as the width of the best elimination order that we call it complete elimination order. The complete elimination order is an elimination order that involves all the network variables. So let's take a look at another example and see how it differs from this one. So here is one first and non-obvious observation that the number of nodes that we have in a network has no effect on the tree width. So we expected that larger networks will be more complicated to make an inference. So that's the general intuition that we have. It tends to be true because larger networks tend to have more connections and possibly parents, nodes with more parents, but that's not always the case. So here we have two networks. The left one has half the number of variables of the right one, but both of them have tree width equal 1. So this is one first interesting observation, that is the difficulty that's imposed by the network doesn't come from the number of nodes, it comes from something else. Let's continue to take a look at some more examples. So here is something that we are expecting, that the number of parents per node has a direct effect on the tree width. So if you look here, we have two networks. They are very similar, but one has tree width equal 1 and the other one has tree width equal 2. And the difference between them is the fact that the right one have one node with a larger number of parents than the left one. So if you look here, this guy has one parent and one parent, one parent and one parent, one parent and one parent. This guy has one parent and this guy has 0 parents. But here, these have 1, 1, 1. This one has 0, but this guy has 2 parents and this one has 0 parents. So one interesting observation is that the number of parents, if the number of parents can reach k, a number k, then the tree width is no less than k. And it will be very simple if the number of parents per node was the only criterion that would influence tree width, but it's not true. Something else that also influences tree width is loops, right? And take a look on here. Again, we have two networks. One has tree width equal 2, the other one has tree width equal 3. Let's take a look, and the difference between them is that the right one has some more loops, so they introduce 2 more edges and loops together with those edges. If we look at the number of parents per node, it should be the same thing. So the maximum should be 2. So 1 here, 1 here, 1 here, 0 here, 2 here, and 0 here. And here we have 1, here we have 2, okay, here we have 1, 2 again, here we have 1, 1, 0 here, 2 here, and 0. So if we look at the maximum number of parents per node, this continues to be 2 for both networks. But because we introduced some loops, the tree width of the right network is 3 and the left one is still 2. Let's continue looking at a few more examples. And again, our life would be much easier if we just had to count the number of parents per node and the number of loops in a network and do some form of computation and get the tree width, but it's not that simple, unfortunately. So another observation is that the number of loops per se does not have a genuine effect on tree width. And we can have one example here. We have 2 networks. Both of them have the same tree width, that is 3, but one of them, this on the left, the first one, sorry, there is a typo here. The first one has more loops than the second one. So it's not just the number of loops, but also the nature of the loops and how they interact with the remaining nodes and edges in the network. So it's interesting to try to identify some classes of networks where we can easily compute the tree width. And one of those classes is called the polytrees networks. So the polytree networks defined as the networks where we have at most one indirect path between every 2 nodes in the network. So when we do this, we are eliminating possible loops in the network. So if you look at a network and we introduce a loop, what we are doing, we have now two possible paths. If we think about undirected paths, we have two possible paths between, for instance, these two nodes. One is following these edges and the other one is following the loop, right? But as we defined that the network cannot have more than one indirected path between two nodes, we are eliminating the loops. So we call these singly connected networks. It's another name for the polytrees networks, and it becomes simple to compute the tree width because the only factor that will affect the tree width is the number of parents. So if the maximum number of parents is k, we know that the tree width of the polytree is also k. Another class of networks that we know how to compute the tree width in a very simple way is called the tree networks. These are polytrees where each node has at most one parent. So as we know, the polytrees, the only factor that affects the tree width is the maximum number of parents. If every node has one parent, we can conclude that the tree width will be at most one. So we have here two examples of tree networks. Both have tree width equal 1 because if you look at the number of parents that we have, you're going to see that the largest one is going to be 1. So both of them have a tree width equal 1. And just to give names to everything that we are looking at, we call the multiply connected network, the network that is not singly connected. So in other words, is not a polytree. So these are two examples of multiply connected networks, this one and this one, and we can see that they are not polytrees because they have loops. Therefore, it's going to be more complicated to compute the tree width of those of this class of networks. So now we have a good understanding of what is the tree width and how it can affect the performance of the variable elimination algorithm. But a question that is interesting to pose is that if we can change the network structure in order to have a simpler structure that will improve the performance of the variable elimination algorithm. And the answer to the more general question that is always possible to do is no, because if we change the structure of the Bayesian network, it will also change the answers that we will provide to the queries. So in general, we cannot change the structure in order to make it simpler. But if we have one specific query, we can change the structure of the network for this query in a very clever way that the answer for the query will be the same. And now we're going to take a look at how we can do that. So the general idea is that the network structure can be simplified based on the query structure. So that is very important. We cannot do that in general. We cannot simplify the network in general. We can simplify a network given a query. And based on this query, we simplify the network in a way that we will still have the same answers for that query. So the query will be a pair Q and E. So Q are the query variables and E is the evidence. And we want to compute the probability of Q and E together. So we have several cases here. So one is that we can make the evidence an empty set. So we will provide no evidence at all, and we will compute the P of Q only. So this is what we call the prior marginals. So we have no evidence. These are the prior marginals. It's the first case that we studied in our previous videos, and we can answer with the algorithm that I'm going to see here. That's merely an extension of what we have seen before, so it's going to be very similar to the variable elimination algorithm that we saw before, but we can still answer this query. Another query that we can answer is that when we make an empty set for the query variables, we will answer what is the P of E. That's the probability of evidence. And we can also, of course, answer the posterior queries. So we are interested in the posterior marginals. In this case, we are wanting to compute the P of Q given E, that we can get it from here to here by just normalizing the numbers in the resulting factor. So we haven't seen this before. So the idea is that the complexity of the inference can be affected by the number and location of the variables in the query. So these two sets of variables here will affect the performance of the algorithm. And we're going to see two transformations, one that eliminate edges and the other one that eliminate nodes. And we see that these two transformations will not affect our ability to compute the joint marginal, the probability of Q and E. And the one first transformation is pruning nodes. So the idea of pruning nodes is very simple. We can prune any leaf node that do not belong to the query or to the evidence. So for instance, we have this network here, and we have two leaf nodes. The leaf nodes are the nodes that have no outgoing edges. So we have this leaf node here, and we have this leaf node here. These are the two ones that we can initially prune. If we prune a leaf node, some other leaf nodes may appear. In this case, we can recursively apply this idea until we get into a situation where we cannot prune nodes anymore. So let's take a look on two examples. So the first example, we want to compute the probability of B and E. And so we're going to operate on this top network here. And this top network, top here, sorry for the mistake, it has a tree width equal to. So yeah, we don't know exactly what is the tree width. In order to compute that, we would have to find what is the best elimination order and calculate the width of this best elimination order. But we expect that it's going to be at least 2, because this node here, it has 2 parents. Right? And all the remaining ones, so this one has 1 parent, this one has 1 parent, this one has 1 parent, this has 0 parents. So we expect to be the true width to be at least 2. So in fact, it was computed and it is 2. And now we want to compute the query. Let me just erase this. We want to compute the query, the probability of B and E. So we observed B. So we are interested in B, right? So this is going to be a query variable. We cannot prune it. And we are also interested in E. It's also a query variable. We cannot prune it. So when you start pruning, the only leaf node that we have available that can be pruned is D. So we're going to come here and eliminate D. As we eliminate D, B becomes a new leaf node, but it belongs to the query set Q. We cannot remove that. E was already in the query set, so we cannot remove it as well. And the other nodes all have outgoing edges. So C and A, they have outgoing edges, so they are not leaf nodes. So they cannot be pruned. So the only node that can be pruned is D. In this case, just pruning one node that's D, it was enough to reduce the tree width to 1, because now we know that this is the resulting of pruning the node D, and this network is a polytree, and it has 1 parent here, 1 parent here, 1 parent here, and 0 parents here. So it's a polytree where the maximum number of parents is 1, so it has tree width equal 1. Another example is that we are interested in the query that has only the variable B. And so the query just B, and is going to be the second case here. And so in this case, we have 2 nodes. This is the only node that belongs to the query. We have 2 nodes that we can prune. So we start in pruning D. Okay. Now we prune E. That's fine. But C becomes a leaf node, and we can always prune C. But we cannot prune A because A has one outgoing edge that goes to B. We cannot prune B because B belongs to the query set. So these are all the nodes that we can prune. So the resulting network is going to be just this. So just A pointing to B, just 2 nodes, and also poly3 that has a tree width equal 1 because this guy here has 1 parent and this guy has 0 parents. So one interesting question is why we can prune these leaf nodes and that will not affect our ability to compute the query. And the answer is actually very simple. So if you think about the variable elimination algorithm, it will eliminate all the variables that do not belong to the query, right? So all those variables that do not belong to the sets Q and E will be eliminated. And the elimination process, we know how it works, is basically sum out the variables. So we do a summation and eliminate the variable. But what happens when we sum out some leaf variables? So variables that belong to the leaf nodes. So we have one example here for D. And this is the CPT for D given its parents B and C. When we sum out D, what do? We take all the matching instantiations of BC and sum over the values of D. And so we're going to sum these 2 rows. For those 2 matching, we're going to sum 2 rows. And we keep in doing this for all these pairs. And the resulting is basically this guy here. When we eliminated variable D, we figure out that when we sum out a leaf node, the resulting is a factor that is composed by numbers 1s. And this factor will be multiplied by the other factors, but it will not affect the final computation because these are all 1. So what we are doing is sum out the variables, let's call it a variable x, from P of x given U, being U the parents of x. And this sum, they're going to be 1. And in the variable elimination process, this thing can happen in, for instance, in a factor f1, where we have x and u. And that's going to be multiplied by other factors that during the variable elimination process that also have the variables u. Let's call it u1, and another factor that has, and not just u1, but u1 and other variables, and another factor that has u2 and things like this. So suppose that u1 is one of the parents of x, u2 it's another parent of x, together with other variables, their own parents. But the important thing is that when we eliminate x, we get this guy here that is 1. Or at least we can interpret that as 1, but it's going to be a factor that has all positions equal 1. And this factor in the variable elimination algorithm will be multiplied by other factors that have those variables here that are the parents of x. During this process, when we're going to eliminate the next variables, we're going to multiply this factor that has 1 by the other factors, and the result is going to be equal to the other factor, so we do not change anything. So we can eliminate those leaf nodes without any issues, as far as they are not part of the query or the evidence variables. Alright, so I think that is a good moment for a pause. Let's take a break and we'll continue discussing pruning, but now with edges instead of vertices. And that's going to conclude our discussion about variable elimination. See you soon.